Hey there, welcome back. This is lecture 4 of the Fundamentals of Electrical and Computer Engineering. This time we are talking about how to simplify kind of messy resistive circuits, so circuits with a lot of resistors in them, how to convert sources from either voltage to current or current to voltage, and then recognizing special circuits. All of these are tools that we use to kind of speed up the process of analyzing circuits. These are some of the most common tools we use because, I don't know about you, but I want to spend less time doing math. So we use these shortcuts and they help us out a lot, especially when we're talking about the analysis methods we learned last week. So last time we said that Kirchhoff's current law, right? When we apply Ohm's law to Kirchhoff's current law, it gives us the node voltage. The node voltage method, right? Where we pick out a node where there's a bunch of currents going through and we look at all those currents and we get an equation that gives us the voltage of that node and of other nodes in, however complicated the circuit may be. And we also looked at how applying Ohm's law to Kirchhoff's voltage law gives us the current mesh. Current mesh method. And that's the one where we look at all the different device voltages, so the voltages across various different devices in a single loop, and we see how they relate through current. And then we get a value for that current loop. And again, we repeat this throughout the whole circuit. We get all the data. We now understand what we're looking at. And that's kind of the point of analyzing circuits, is to pull data out of the mess of squiggles so that we know what we're looking at. So, part of doing that is sometimes we have to simplify impedance. And remember how impedance is kind of the same, or we're treating it very much the same as resistance. There's not two R's in resistance. Right? Because impedance is resistance and reluctance. And resistance is the real number. So we like to use it because it's not imaginary numbers math. So, last homework, we saw this circuit. And we saw that node A, is kind of a mess, right? So, node A, it's labeled here. But we also see that this current source is going into it. And, well, since there's nothing going on in this wire, this point is also node A. So, these two resistors are inside of node A. So if we draw it out as one condensed node, we'll end up with that source, right? Source attached. Then we've got R1, right? R1. Then we've got this branch has both R2 and R3, so R2 and R3. And then we've got R4 attached, so R4. There's a lot going on. Well, let's look at the node equation there, because actually, you have already done a simple circuit equivalent impedance. So, let's look. So, we're going to have 0 equals, and then I1, right? Because that's what's coming in to A. Then we're going to have minus A, right? Minus A minus 0, right? Because it's A to ground, so 0, all over R1. Then we're going to have minus A again, minus 0 ground, right? And then we're going to have both of these, because if we're going to go from A to ground, we have to go through both resistors. So we're going to say R2 plus R3, right? And then we're going to say minus A minus B, right? Because we're starting here and we're going to that node, B, all over R4. And that's quite messy, so we're going to remove some of that. So the trick here, I want to bring attention to this term. This term. Because specifically here, you've already done an equivalent resistance here. So, by nature, we had to find equivalent impedance. So I'm gonna rewrite this term specifically. The current across this branch equals A minus 0, so the voltage at A minus the voltage at ground, all over R2 plus R3. So why don't we just replace that then? Right? We can just use variables, so let's just use variables. Let's say that we replace R2 and R3 with some REQ, our equivalent, that produces impedance that affects the circuit in the same way as having both R2 and R3 in the same place. So that's kind of what it means to do equivalency. So we're just going to have REQ, and we've decided that REQ equals R2 plus R3. It's really just a matter of substitution. This is what it means to find an equivalent. So, there are two forms of equivalence brought to you by our very unfriendly neighborhood serial killer. There are two forms of equivalence: serial, or series, and parallel. We don't want to meet this many Freddy Kruegers. I don't think anyone wants to meet one. So, there are specific equations to get series and parallel resistance. Or, nightmares. For series, we have R equivalent equals just the sum of every resistor in series. I wrote this out of order, I apologize. But it doesn't matter because addition is commutative. So series means that the positive end connects to the negative end of the last term. Plus negative, right? So the positive end of R2 connects to the negative end of R1. The positive end of R3 connects to the negative end of R2. The positive end of R4 connects to the negative end of R3. These are in series. When you have something branching, so like this is no longer in series, okay? Then we're looking at parallels. Parallels are where all of the positive ends are tied together and all of the negative ends are tied together, generally at ground. So the equation for parallel, that one's a little bit more complicated. It's not super bad, but it is fractions and it generally just drives people up a wall. So it is 1 over the following, okay? It is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So there are, technically, this is generally taught as 1 over REQ equals 1 over R1 plus 1 over R2 ... right? This is horribly confusing. Just write it this way. Trust me. Just always remember that the sum of these is also in the denominator. You can also write it like this. To the negative one, right? Because that also means that it's in the denominator. Just don't forget to do this. Otherwise the numbers will come out very, very small. And also incorrect. So let's do an example. First of all, we want to start with the elements that are the least involved. What does that mean? Well, we are looking for elements that have very few connections, like this one, for instance. This one only has one connection. Plus negative, plus negative. It's in series with this one, so we can go ahead and find one equivalent resistance. EQ1 equals, they're in series, right? Negative to positive. So it's going to be Z4 plus Z5. And that's it. Alright, so now we can redraw the circuit and repeat. And we'll do that as many times as we need in order to get to a simpler circuit. I'm not going to keep copying the pictures, I apologize. So we have simplified one set of our serial killers. And that is here, right? This one becomes ZEQ1. This one's still Z3. This one's still Z1. This one's still Z2, right? And this is still some voltage source. You'll notice that the voltage source doesn't really matter while we're doing equivalent resistance, because the resistance is a material property, right? It's not dependent on the voltage attached to it. So the next thing we do, right, we've just simplified our serial killers. So now we're going to deal with some parallel killers. And we can write that like this. Z3 parallel to ZEQ1 is, ZEQ2. And we can solve that out, right? So we can say 1 over Z3 plus 1 over ZEQ1 to the negative 1. Which, if you do the whole algebra stuff, you end up with this. ZEQ1 times Z3 over ZEQ1 plus Z3. Okay. Next step, right? We can redraw that again. So, source Z1, Z2, and ZEQ2, right? Because that is going to be this. Well, now we're back to having only serial killers. So our equivalent circuit is going to be this, where the equivalent killer is going to be Z1 plus Z2 plus the whole mess from up here, right? And I've already solved that out, so you don't have to see the algebra for it. But it's going to be Z4 plus Z5, Z3 over Z4 plus Z5 plus Z3. in practice, you're probably just going to find numbers at each of these stages. I don't expect you to go through and find an equation to end all equations and then plug in everything at the end. You can just calculate as you go. Just make sure you keep like 3 digits of accuracy while you're doing this. Three digits past the decimal place. Just to make sure that the calculator doesn't round things funny. So, anyway, in practice, most often, you are going to apply equivalent impedance to only parts of a circuit, right? It's not usually practical or necessary to get the whole circuit down to a one element and one source, okay? It also changes some things. So like you can't get the current over R3 or Z3 anymore because Z3 doesn't exist anymore. You have an equivalent. And the current here is going to be the current coming out of the source. It's not going to be each individual device current anymore. So like there are pros and cons, but overall, it's a good way to simplify parts or, all of a circuit, and simplifying a whole circuit's good practice. So, next really cool tool we've got is converting sources. So, this one is comes from applying Ohm's law. Applying Ohm's law to these sources in a circuit. So, I don't know about you, but I do not like seeing current sources because in my head, I don't really know what that is. Okay? I know kind of what a voltage source is. That's equivalent to plugging something into the wall. Or, plugging up a battery to it, right? Those are sources of voltage. I can imagine those. But I don't like current sources. What produces current? I don't know. It's a way to model things. So the reason we see them is because it's a way to model things. But it's really hard to nail down, all right, this current thing, this box produces current without being a voltage source. Because, Ohm's law connects voltage and current through resistance. So we're given a circuit with a current source against all of our preference. And we know through Ohm's law that current, that I, is related to R. So we can just solve for the voltage. We know it exists. Current source. So we can just solve for it. The voltage across this resistor is gonna be IR, right? We can just use that, okay? We can use that to make an equivalent source. An equivalent source. That's the important one there. So, but it has to be with a specific circuit shape. So, this comes down to a concept. This is a simplification of a concept that is known as Thevenin and Norton equivalence. And we're not going to go deeply into that. We're going to look specifically at this simplification because this is kind of a specific set of theorems that you don't really need them at this level. You don't need them to look at Arduino circuits or things like that. And that's really what you're going to be coming across. And that's kind of what the goal of this class is to give you enough circuits that you do not feel intimidated by, say, senior design requiring circuits and things like that. So we're looking specifically at these two shapes. Cough, cough. This one's related to Thevenin. This one, nope, wrong directions. This one's related to Norton. This one's related to Thevenin. Don't be surprised if those come up, or if you hear them later. You can now trust that they have to do with converting sources and finding equivalent and very simple circuit models for more complicated circuits. But right now we're just looking at source conversion. So shape one. We got a current source. A current source, that's the source type. And its resistor is in parallel. This is important, okay? In shape 2, the source is a voltage source, and the resistor is in series. So, if you have a voltage source and only a parallel resistor, you cannot do this. If you have a current source and a series resistor, you cannot do this. It has to be these two, okay? And they convert between these two, okay? Using Ohm's law, we can convert the shape of one to another, but only if there is a resistor in the right place with respect to the source type. Because the other thing here is you can't just convert a voltage source to a current source. There has to be something to relate them, and we know what relates them, and it's impedance. So, usually you'll want to do this to convert current sources to their equivalent voltage. Their equivalent voltage. So, and again, this is because current source is rude in brain. Also because it makes mesh analysis not possible. You cannot apply mesh analysis. So, here's an example. We're going to find V out using mesh analysis. That thing that I just said we couldn't use if there's a current source on a branch. Cool. So we need to convert this resistor, this source, right? V out is so first of all, let's just look at the whole circuit. Let's see what's going on and make some plans. So we need V out. V out is here. V out is the device voltage of the 2 ohm R4 resistor, right? It's the voltage across this resistor. The next thing is, there's a complicated part, and it's the 3 amp current source. Right? It's this guy. It's here. And that's because the branch with the current source, we can't use mesh analysis. So we need to do a source conversion of the current source. We need to convert it to voltage. Right? So, step 1. Find the source resistor pair. So we need the right geometry. We need the parallel resistor to the current source. And we got it. It's right there. It happens between point A and here. The terminal that shows us V out. So we're just going to apply Ohm's law to that. So we've got this here and like that. And, you know, if you draw it sideways, or like the way we were introduced to this, it looks like this. It's the same. It's the right geometry. So we got V equals IR. So we got 3 amps times 5 ohms is 15 volts, right? So now we need to redraw the new source with the same resistor. All right, so that feels really weird in their new place. So now that we have this voltage, we can redraw this as a voltage in series with a resistor. And the voltage, plus minus, actually the plus minus is supposed to go into the circle. There we go. Plus minus, there we go. In series with the same resistor. So still going to be 5 ohms. This one is going to be 15 volts though. And it's because it works out correctly. So basically we figured out as engineers that through the magic of Ohm's law and Kirchhoff's laws, we can just do this. We can convert this. So something we need to note, the positive end of the source, of the voltage source, goes in the direction of the head of the current arrow, okay? So how we drew this arrow going from right to left, well, so that means that the positive end has to go on the left, where the direction of the arrow was going. I know that this is contrary to what we set as our convention, but this is how the math works out, and we are using the math of our forebears. So this is a shortcut, so just trust that it works this way. You're more than welcome to do the math for it to prove it to yourself. But this is a shortcut. So also you don't have to prove it to yourself. So now we can just apply mesh analysis to find I2, right? Because all we need is I2. If we got I1 and I2. All we need is the second loop current, because we already have the resistance of this device, so we can just get V out that way. So, calculate V out. So, a challenge! Go ahead, pause the video, and write out the equations. I'll give you the answer at the end, or, when you come back from being paused. But I'm not going to give you the algebra to go through it. I'm just going to give you the equations and the number answer. So go ahead, take some time, do this for yourself, and see you in a second. All right, so welcome back from pause. We're going to get 2 equations out of this, right? 2 mesh analysis equations. So it's going to be 5 minus R2, I2 minus I1, minus R1, I1, and then second equation is going to be this. I2, whoops, here we go, close parentheses, there we go. All right, and you're going to find V out as 5.83 volts. So I strongly suggest going ahead and working this one out yourself. It's just really good practice. And, might be something that shows up on tests and things like that. Because it's a good test problem, I think. All right, so third shortcut we've got is recognizing special circuits. So in the spirit of simplifying analysis, let's look at something called voltage divider and current divider. Voltage divider and current divider. So these are two specific shapes of circuits that we already know the math for, and we've already done the math for as a practice, as a field, so we don't need to do it again. You can do it again. They're very easy to derive. But you don't have to derive them if you can recognize them. You can just apply the equations, and that's what's really cool about these. So, these are special circuits where current or voltage is divided due to the arrangement of the impedance sources. And yes, by that I do mean the resistors, but also anything else that might cause impedance. So, this one we look at is voltage divider. And we see that we've got, because of Ohm's law, right, we've got device voltages across Z1 and Z2, right? So we've got V1 and V2. And you'll note that I didn't put a real source here. I'm just indicating that there is a voltage here. Well, that's because if you've got some mess causing a voltage here, you can still apply voltage divider. But so this is actually the simplest shape. You find this, or this in a circuit and you need the voltage on one or the other, bam, you are in business. Well, same thing for current divider, right? So current divider, you've got currents. There's a current coming from this source. We'll call it I source. And then you've got each stem has a current, I1 and I2, right? And we know that from Kirchhoff's current law, right? So current divider happens in a parallel circuit. And it is due to current law, right? Because this is effectively one current coming into a node, another current, and another current. That's the same current T shape we've seen multiple times so far. Voltage divider, that one is a series circuit. If there was another branch here, you could no longer apply voltage divider, because these are no longer devices in series. Now, if you could simplify this down with equivalent resistance to get it to be series, then you could. But as it is, it has to be two series devices to get that good plug and play action going. So, voltage divider due to voltage drop. So why is it due to voltage drop? Well, it's because each of these devices has a voltage drop or device voltage, that there is a point where there is a unique voltage here that is not the source, and it is not ground. Even though there's not really a node here, there is a unique voltage here, because the first resistor changed, or, ate some of the voltage. There was a voltage drop. This is a great shortcut. This one shows up so much. I cannot understate how much I have seen voltage divider over my career as an electrical engineer. Okay, current divider is a little less common because usually it's just easier to apply node analysis at that point, but voltage divider, huge. Okay, so voltage divider is used to get the voltage across either the resistor, or either of the resistors. There we go. And it is equivalent to saying it's the device voltage. We're getting the device voltage of either resistor, okay? Versus in parallel, or in current divider, we are getting the current across either resistor. And this is called the branch current. Or the device current, but is specifically looking at the branches. If you had multiple resistors here, it would not be this. Well, I guess technically it would be, because current is the same in parallel. Yeah, so it's effectively the same to say branch current or device current. So, how do we get them? What are the equations? So, V1 in voltage divider is going to be the source times the ratio of the resistance of the first resistor to the total resistance, R1 plus R2. And V2 is R2 to R1 plus R2. And this literally comes from applying KVL to this circuit and then converting the resistor you want the voltage of to voltage using Ohm's law, okay? So it's KVL plus Ohm's law. Now, current divider is visually similar, but make sure you take note, okay? For I1, it's the ratio, it's I source, right? I source, and this is I1, times the ratio of resistor 2 to the total resistance, okay? And then I2 is the source times R1 to R1 plus R2. Now, if you magically had more than 2 devices, you could also do that. You could also just apply an equation. It would be the relationship of the resistor you are looking for to the sum of the resistance, okay? But it's most common to just see these in 2-element form, and that's what I'm going to teach you because it is the most useful one. Anything more complicated, it's probably worth using a different analysis method or not using a shortcut. So, anyway, comes from using Ohm's law after applying KVL. Current divider comes from using Ohm's law after applying KCL, okay? So effectively, we solved for an unknown, but it wasn't in the form we wanted, so we used Ohm's law to get the value of that unknown. And I'm very, very happy to derive these for you, either in office hours or to make a separate video. I just need you to let me know that you're interested in it. I think it's a lot of fun to make these derivations, but they also do take a good chunk of time, and I didn't want to force you through them. So, because frankly, you don't need the derivations to use these shortcuts. That's kind of the point of the shortcut. That being said, I've always learned better using the derivations, so again, just let me know. I'm happy to get that for you. All right. So, let's do an example. Let us look at this. So, this says the voltage across Z2 needs to be at most 3 volts. So we know it to be 3 volts. If Z2 is 1K, what must Z1 be? So basically, we were told we know what this device needs as a voltage. Oh, I'm sorry, I labeled the wrong one. We know what this one needs as a voltage and what impedance it puts out. We need to know what this resistor needs to be in order to ensure this device doesn't get fried. This is a very practical application. I have actually had to do this on Arduino circuits to make sure I didn't kill LEDs and servos. So, yeah, useful. This is actually useful, applicable stuff. So, we're gonna look at V2 equals, because that's the voltage across these that we were given, okay? And we know that voltage divider relates all the voltage in the circuit, or at least the two related voltages in the orientation. So we're going to have V2 equals V source times R2 over R1 plus R2. This is the equation we're going to use. We're going to plug everything in, and then we're going to solve. So we've got V2 is 3 volts. Then we've got V source is 10 volts. And then we've got R2 is 1K. Then we've got R plus 1K, because that's the equivalent, or that's the total resistance, right? The total impedance. So 3R plus 3K equals 10K, right? We're just multiplying this stuff across, simplifying things down. 3R equals 7K. So R must equal 7/3 K, right? Or, sorry, wrong symbol. Or about 2.3 kilo ohms, or, 3.3. It continues. So, easy peasy. Just plug it in, solve for the thing you need, bam, lava lamps. So, how do we then choose a resistor for this, right? Because, practical example, this is a thing that I've had to do. And we know that we can read resistors, but can we choose them? So, the thing is that 2333.3 is really specific. And it's too specific to be able to choose a resistor on. So we're going to need to round up. And we do that because 3 volts is the maximum. We were told that, right? We were told at most 3 volts. That means that anything over 3 volts is probably going to damage our device. So if we put in too much resistance, that'll be okay. The device will most likely still function. If we put in too little resistance, the device is going to break. So we have to choose a resistor that has more resistance than the number we calculated. So we can deal with the device having a little less than 3 volts if it means that the device is not going to fry. So the resistor can be a little larger. So what are we going to do? We have a couple of options. So up here we have a 4-band resistor. Down here we have a 5-band resistor. These are considered precision. They are more precise because they have more, well, they are more precise. They're made that way. These ones are less precise. These are more common. So let's figure out what rounding we could do to make either one of these work. Well, so 4 bands only have 2 digits and a multiplier. So that means that we have to round up that second digit. And that's the most accurate we can get with a 4-banded resistor, okay? So we're going to end up with 2400. So about 2.4 kilo ohms. We're going to do that by first saying, all right, cool beans, I'm going to choose the tolerance, and we're going to choose the lesser tolerance. It's most common to find the plus or minus 5%. 1. So you'll have to take that into account. What is plus or minus 5% of the number you chose. Specifically here, you'll care about the or minus section, because if it's under the threshold number, then we're going to have a problem with our device upstream. But for now, we're just doing this in mock. We don't need to be too specific, but just to understand. So, first thing we're going to do is we're going to say we got 2 as the first digit. 2 is red. So we're going to choose one with a red band in the front. Then the number we've got is 4, which is yellow, and I'm going to try and pick a yellow that is not our gold. That'll work. There we go. Yellow. We don't have a third digit in a 4-band one. We have a multiplier. Well, 2400, we need 2 zeros, so that's going to be the 100 multiplier. So we're going to have another red band. And that's it. You'd find a red, yellow, red, gold resistor and be able to plug it into your circuit. Okay? What about if we had access to any precision resistors? All right, well, so we don't have to round at the second digit here. Tens, hundreds, thousands. There we go. At the hundreds digit, we can round at the tens digit because we have 3 decimals and a scalar. So we're gonna say this one, for the precision one, we have the first digit is going to be 2 because that's the same. Then we can pick 3 because we don't have to round this one. Then we do have to round the third digit here up. So we're rounding at the tens digit. So we now only need 1 0 to fill. So we're going to pick brown, right? So this one's going to be about that should have been a 4, not another 3. I said round, and then we didn't round. There we go. So it's going to be 2.34 kiloohms, and that's more specific. You can see how this one is slightly closer to the number we calculated than the 4-band resistor, right? So let's go ahead and pick it out. So same color codes match, so we're picking 2 as our thousands digit, right? So it's going to be red. Now we're picking 3. 3 is orange, so we got an orange band. Then we're picking 4, which is yellow. We're going to use that yellow, that's not gold. Now we need the third digit, that is the third digit, which is 4. And now we need this 0. So we need brown. We need a real, honest to goodness, brown. How are we going to get that? There we go. Nope. There we go. Now we need brown, because we only need 1 0. We only need 0 in the tens, in the ones digit. There we go. So you're going to pick a red, orange, yellow, brown, gold for the precision resistor, okay? More than likely, you're just going to have a vat of resistors, and you're going to pick something that is the closest to this without going under. Unless you were given it has to be at minimum this, go ham. In which case, it has to be, you have to make that voltage at minimum for the device to function. Some devices are like this. Looking at you, tower servos. Also LEDs. But anyway, this is how you would go about figuring out which actual resistor to plug into your circuit here. So let's look at another example, and let's look at the current divider example. So in this case, we've got an LED. The LED needs a current of 5 milliamps to operate. So this I has to be 5 milliamps. And this is an LED, and I apologize. That's it. I apologize. So these arrows mean that it's emanating light. An LED is a diode. It is an encapsulated diode, and it is an encapsulated diode that produces light. That's what this symbol means. There's a reason I didn't explain it until I had to. Let us unpack what we've got. So we have an LED, but we don't really care that it's a diode right now. Our LED can actually be modeled. It can actually be modeled as just its resistance right now. So first of all, I forgot to read the problem statement. Find the internal resistance of the LED. So it's a diode, an encapsulated diode. An encapsulated diode with that emanates light, and it has resistance in there. Yeah. Okay. So we're going to say its resistances are LED, right? And we're going to stop looking at this. We're going to look at a familiar symbol. We're going to look at the resistor because we don't really need any of its diode properties right now. We may or may not get to explaining the diode properties. So for now, we're just going to look at this like a resistor. So we can just redraw the circuit. And we are going to redraw the circuit. Poorly. Apparently. Alright, there we go. We got this R, and then this is our LED now. This is our LED. Our and R. It's going to have some current. I LED. And of course, there's going to be some current I1, and we know there's some I source. And I already told you this is the current divider example, so you were not surprised that I set this up for current divider. So we are going to then just apply the equation, right? So we know what current has to be here. We just need to find the resistance here. Well, to do that, we're going to apply current divider because we weren't given any voltages and I don't want to find them, okay? That would be complicated versus I can just throw one equation at this and be done. Instead of, I mean, we could look at this with KCL and we could say, all right, well there's I source and there's I1 and I LED and I don't know what this voltage is. I know the down here is going to be ground, but we weren't given a voltage to start with. So this whole thing becomes just more work than it has to be. So instead, we're going to say I2 equals I source times R over the sum of resistance, right? R plus R LED. And then we're going to plug stuff in. We started with I2 because I2 is I LED, right? So we got that 5 milliamps that we were told this LED requires. Then we've got the 10 milliamps of the source times this 3 ohm resistor plus over 3 plus our LED, right? And so we just do the algebra thing. And we say we got 5 RLED plus, 5 milli, and then we've got 15 milli, there we go, equals 30 milli, right? So 5 milli RLED equals 15 milli, so RLED equals 3 ohms. And that's it. Fast, simple, easy calculations. Because we recognized that, oh hey, this is in a shape I know how to deal with. I don't have to touch voltage at all because I can just, I I know that these things are related, and someone's already done the calculation to find this equation, so that's it. We're good. We're done. We are in business. So I firmly suggest trying to apply these tricks. They are convenient. They are also simpler calculations, so they're less likely to make simple carry errors and things like that. It is good strategy. So next time we're gonna finish the analysis tools, and then we will move on to more complicated circuits after that. So, but next time, look forward to return of mesh and node analysis. Alrighty, great job. Go take a break. Go eat some food, some real food, not junk food. Alright, anyway, have a good day. Bye-bye!